Hello and welcome to episode 4 of C++ Weekly. I'm your host, Jason Turner. Once a week, we'll pick some topic of interest in C++ and dig into it with some live coding. In this episode, we're going to look at modernizing some variadic template code from ChyScript. Or more to the point, we're going to look at modernizing some code that should have been variadic templates, but was not. So we have a concept in ChyScript called an exception specification. It is a C++ helper wrapper for us that takes a list of possible types that might be thrown during your script execution and can unwrap them for you and throw the appropriate expected type to C++. So in this particular case, we are testing that we can throw an integer and then catch an integer inside of C++. Or similarly, that we could throw a double, catch a double, or as we see here, we could throw a runtime error and catch a STD exception using automatic conversions to base types. So the exception specification needs to take an arbitrarily long list of potential types that might be thrown so it knows what types to unbox from the scripting environment and throw back to C++. We have already compiled ChyScript and can execute the test and see that all tests pass here. This code is implemented in the dispatch kit exception specification header. And right now, we can see the interface to it, which is the exception specification function, has 1, 2, 3, 4, 5 different implementations. Each one instantiates a different version of the exception handler impl class, which we can see we have exception handler impl 1, impl 2, impl 3, impl 4, and impl 5. And this is clearly a lot of code duplication. So let's look at what needs to be modernized and updated in this code to make it more C++ 2014. And for a little bit of history, this code has always worked just fine with up to 5 exception specifications allowed. So there was never really any motivation to update it, and it just basically got left behind. So starting with the exception handler base, we should be using equals default here instead of an empty braces. That wasn't being used because not all compilers supported that. And because we have specified that the base class has a virtual default destructor, we have no need to specify the destructors in the implementation classes at all. So let's remove those. We also know, since we're moving this code to C++ 14, that the ChyScript override macro is meaningless. So we can just change that to the override keyword. And since we have override specified now, in all cases, we don't actually need the virtual keyword anymore. Now, as a side note, I'm not going to necessarily bother doing this in all cases, But we could also specify each of these implementations as final, which gives the compiler a hint that we do not tend to further derive them at all. And it could theoretically, in some cases, use this to better optimize the code. But let's get more down to the point here. We need to make this into a variadic template because it is silly for us to have this many different copies of the same code. So let's look at what we need to do. If we are going to get rid of all these different versions, we need to figure out how to have a single version. So we're going to make a variadic template specification, and we'll have just the one exception handler impl that derives from exception handler base. And we know that it needs to have a single function method that takes a boxed value that we want to try to cast to each of the possible different exception types. So this is our handle function. So we know that we need to throw the type, call throw type for what? For something. And if we can figure out what that something is, we don't need any of these other versions of our struct anymore. So how do we make it throw exactly one of these and none of the others? So we could create a new function Let's make it a free function. Throw each thing, shall we call it. It needs to take a initial item and then the rest of them. So we can say in here, throw type of t1, we want to try the first one, and pass in our two objects. And then we want to throw each thing for the rest of the possible types, and pass along our boxed value and engine. This way we know that each of them will be executed in order as expected and peeled off one by one. So we can then call our throw each thing with our set of types, our boxed value, and the execution engine. Now, that takes this code and makes it so we have way more implementations than we need also, because we have 1 through 5, and really we just need the one. So we want to construct a detail exception handler impl of all of the test and types. Now I expect this to work. To compile on the first try, we will see if it does. Use of undeclared identifier throw type. Ah, that should have been obvious. That's because throw type is a protected member of exception handler base static. We're going to be moving in a different direction from this code ultimately. So let's just go ahead and make that a public static member or actually, let's try this. So while that's attempting to compile, we'll see what we did is we made throw type and throw each thing both protected members of exception handler base so that they are then callable from exception handler impl. Error expected semicolon after struct. Semicolon after struct. So much better than the errors used to be that we would get from GCC. Okay, that looks like that's probably going to succeed in building, but I think we might still have a compile error lurking in this code. So as soon as the standard library is done building, we will build our compiled tests and we'll see what they do. So all these recursive template instantiations for throw each thing are potentially not ideal if lots of different versions of our exception specification are being created. All right, that compiled. Let's see how our compiled tests do. There we go. No matching function call for throw each thing. And notice this error is happening specifically when t equals an empty set of parameters. This is a problem with the 0th case. So with this kind of recursive instantiation of templates for variadic template usage, we have to figure out what to do. Do we handle the 0th case where there are no template arguments, which I believe will work? So it will execute throw type, and then it will go to create the next execution of throw each thing with no template arguments. But if it has no template arguments, will it find the correct overload of the function? Unused parameter, that's not a big deal. That's easily fixed. No matching function call for throw each thing because it still thinks that it's trying to call a template and we don't have one. So our alternative is to simply write the first case, if you will. So now we have a version that's expecting exactly one template parameter, and we have a version that's expecting more than one template parameter. And if we take the one version, then we do not try to recurse on ourselves. If we take the more than one version, then we do recurse on ourselves. It can definitely be difficult to wrap your mind around how to use the template type system to get exactly what you want out of it. This should get us here now, though. I was expecting to find an error with the 0th case. Now it's saying the call to the throw is ambiguous. So this is difficult to do. Many cases when this kind of thing is used, you actually are taking a set of parameters that match each of these types, but we're having to only work with the types, and we don't have a set of parameters such as that kind of thing. That can help us peel off each parameter and then use function overload resolution to determine how many parameters are being passed in. Instead, we have to use the template system to determine which function to execute. So I promised at the beginning of this, or earlier in this video, that we're actually going to go somewhere simpler. And I don't mind throwing away this code so far, if for no other reason to point out that this code can get complicated and template metaprogramming can be sometimes difficult to figure out. This is template metaprogramming, by the way, is features that I have to use in the dispatch parts of ChiScript in several cases. And it's actually quite clean at this point. But for this particular case, I always had a difficult time wrapping my mind around how I would use variadic templates for it. And that's one reason why we ended up with all of the classes just being specified 1 through 5 as they were when we started this video. So what solution I ended up settling on is to not even try to wrap my mind around how to peel off each one of these template type parameters. And instead, we know that we need to call throw type for each of the types that were passed in. So we want to use a variadic template expansion that looks like this. This would be ideal. But the compiler does not like that. Expected semicolon after expression, it doesn't know what to do with expansion parameter type packs in this context. But it does know what to do with them in the context of a standard initializer list. So we can actually do std initializer list of what? What needs to go here to get this to compile? And what we can see is that we actually want to take a little trick here that I learned from other people and say we want to take an integer and we want to do an expansion of the evaluation of our throw type of t with the boxed value and the engine and comma 0, and then expand that with the variadic template expansion. This comma expression right here is a little used feature in C++, that basically tells the compiler, we want to evaluate the left-hand side and the right-hand side, and then only return the result of the right-hand side. So the return value, or the type, if you will, of the evaluation of this expression is an integer. So we can say we're creating a standard initializer list of integers, and it is for this expansion. Let's see if I got the syntax for that right. Pretty sure I did. All right, that seems to be compiling. So in general, you cannot rely on the order of evaluation of operations in C++. So if I wanted to do something like call function, and I wanted to say I++, 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 and I equals 0. If I wanted to actually do this, what values get passed to call function is unspecified by the compiler, and you can actually find real differences between real shipping compilers today. So if we cannot rely on the order of evaluation of arguments, how can we rely on this doing what we expect it to do? We can rely on this because the order of evaluation of arguments passed to initializer list is actually well defined as being in the order of left to right. So we know that our types are going to be attempted to be thrown in the order that they were specified by the user, starting with the first type and going to the last type. And the compiler will essentially throw away the result of this and compile it all down to something quite simple and succinct. And it avoids instantiating very many functions because it avoids the problem of having to recursively instantiate functions. So one last note, you'll notice here that we got a warning on line 48, unused expression result. So if you're going to use this trick of using std initializer list to avoid recursive template expansions, you can also just give the compiler a little hint that you don't care about the return value of it, and this works in every compiler that I've tried without generating any additional warnings. So now we have reduced our code down to a single call for exception specification and a single instance for the exception handler impl. And while we're here, we may as well see if there's a few other things we can clean up, because why not? So we can specify that this is a final version of exception handler impl. Maybe that can help the compiler optimize some of the code generation. We can say here that we want to do a this is I might dig into this into a later episode, but we're going to tell the compiler that we're making a unique pointer. And then we're going to cast that to this shared pointer type def. And I have a very good reason for that. Like I said, I might dig into it later. Let's kick off a build of that while we keep looking at the code. Let's see. So this is interesting. We have this static throw type function. I'm missing a header. Oh, no, this code is compiling against C++ 11 at the moment, which is why make unique is not found instead of C++ 14. So I will go back to making this a make shared, and then, like I said, I'll probably give some clue as to why I would have preferred make unique later in another episode. So let's see, this throw type function is only used inside here, so it's potentially making our symbol table bigger than it needs to be because we have too many instantiations, or we have many instantiations of it. So it's possible, you know what? Let's do a quick change to our CMake list. To make this a C++14 build. So we can show one other little nicety that we might want to do in this code. Okay. No, actually, the more I look at it, I don't see another change that I could make. I was planning to make this a generic lambda, but because it does not rely on any of the parameter types, instead it needs an explicit templated type passed to the function call. As we can see here, throw type takes t. Then there would be no way for us to utilize a generic lambda. So I'll leave this video where we are here, and I hope this has been informational. And if you have any comments, as usual, as to the color schemes or anything about the video series that I might be able to improve, please leave me a note. Twitter is one of the best ways to get in touch with me. And the other options are on the Patreon site. So thank you again for joining me today.